Good evening, we are Group 6 and we are presenting on the effects of strain hardening on the flexural and compressive properties of the fiber reinforced clay matrix components. In this presentation, we will have 6 main talking points, which are the introduction, the relation to material science, the methods, the results, the discussions and implications, and lastly, the conclusions. A brief introduction. The chemical structure of a substance is an important determinant of a material's chemical structure characteristics. Small modifications to a compound's chemical structure can have a significant impact on its qualities. In this project, we were able to ascertain how the matrix fiber composition affects the properties of composite materials by creating composites of clay and fiber with various composites, as shown by compression and the 3-point bend test carried out on the various samples.
So, our relationship with material science, we had a chance to learn about malleability, and it's as a result of code working. We also have to learn about like brittle failure and understand how the little voids or a small void can lead to failure. And we also had a good time to discover how rounded notch ones have little effects on the failure of a brittle material compared to the sharp ones. Because we discovered that with some of the bricks that we have, a small crack was actually leading to the failure of the whole brick, like breaking into half for some of our samples that we have. We also had a time to really research about clay being a ceramics or ceramics being made from clay. We also had a research paper supporting it, which we used as one of our references. We also had to like have a chance to see the strain hardening first and how it was really affected, like from the yield strength to the tensile strength. So basically I'll move on to the composites materials. So relationship to material science part 2, basically we are going to talk about composites. So two chemically and physically distinct phases were shown, and that makes it a composite. The continuous phase, which is also called the matrix in our case, was the clay, and the embedded phase, sometimes referred to as the reinforcing agent, because it serves to strengthen the composite where the fibers. And we had a chance to see how the two bricks that we made were different and how strong or how the fibers straighten um, the bricks overall.
Clay ores were physically pounded and sieved into powder, and then the clay was reinforced with fiber. The fiber was cut between 2 centimeters and 3 centimeters long. Only clay was casted for as the control experiment, but the samples itself were 60% clay and 40% fiber. This was volume proportion. Also, when the mixture was made, when water was added to the clay only and the fiber and clay only mixture, this was cold worked for 3 days before being casted. And after they were being casted, they were left indoors for 24 hours to avoid cracking when exposed immediately to the sun. And after the samples were left in the sun for 1 week to dry completely. Then the samples were taken to the MEC lab so that comprehensive testing will be done on the cylindrical samples, whilst 3-point bending test will be conducted on the rectangular samples. So the fibers were oriented randomly. That means it will be stronger in either direction, whether longitudinal or transverse direction.
Okay, so for the results, what we did was we took our results, we took the samples we gotten from the lab, and we went to put them to test. We performed the tensile test and we also performed the flexural test on each of them. So for the cylindrical ones, we performed the tensile test on it, and for the rectangular ones, it was a flexural test. So I'll be taking the rectangular ones first, which we performed the flexural test on. We took the ones with the clay and fiber, and we plotted the graph, and we took the ones with only clay and plotted the graph. On this graph, the one with only clay is the red one, and the one with clay and fiber is the blue one. So as we can see, the blue one expands over like more surface area, it's more tough and things like that. And the red one is just a small part of the graph. The next one we'll be talking about is the tensile test that we performed on for that was for the cylindrical samples. So we took our cylindrical samples that we had done in the mechanics lab, and we took it to the lab to do a few tests on it. We did a tensile test on it, like I mentioned earlier. And here, once again, the blue line goes is for the clay fiber composite, and the red line is for the pure clay composite. So we noticed something interesting about this graph. Like it's not like the last graph, that one was flexural, but this is tensile. And this one is that the blue graph is higher than the red graph, and I think we'll know more about that in the results that will be discussed right after now.
In the discussion, we realized that under fiber alignment, Ferreira in 2011 discovered that 50% of the fibers are oriented in a 10-degree angle from the horizontal, such that we could end up in reality concluding that most of the fibers are arranged in almost a horizontal manner as compared to the theoretical assumption that all the fibers are arranged in an haphazard manner. So in theory we end up having isotropic properties, but in reality uh, we have anisotropic properties being predominant, as the compressing has now forced the fibers to arrange themselves almost in a horizontal manner. There's a plastic flow of matrix stress transfer to the fiber, and this leads to high yield strength of flexural modulus and toughness. So this is the reason why composites have um, a higher flexural strength, toughness, as well as compression strengths. They actually bear most of the load instead of the matrix to bear most of the load, and so this helps in improving the properties I've already mentioned compared to a pure material which is not reinforced. Composites have a high strength to weight ratio because of their low weight, and this has resulted in composites being used mostly in the aerospace or airplane engineering because we can utilize their high strength to weight ratio. Lastly, composites exhibit high compression values compared to pure materials.
So I'll move on to the limitations. So basically our arrangement was random, hence it was isotropic. Like we could have done the longitudinal ones, which could like result in stronger structures, basically tougher ones. But by the time we did it, we haven't learned about it. So basically the effect of the orientation of fiber efficiency was kind of reduced because the ones which are like longitudinally arranged and using the critical fiber efficiency formula could have produced much stronger beaks. Basically, the critical fiber efficiency, we literally were ignorant about the information. The fiber length should be greater than 15 times its diameter, strength in tension divided by the shear stress, which is basically given by F over 2 pi RL. We could have looked also at the effect of change in densities and volume per ratios and see how overall our structure was going to be affected, including the specific structure fracture ratios. So the conclusion, we come to a conclusion that basically ceramics are strong in compression. We noticed it through the results and the discussion that we have. And they are surely affected by minor cracks, like a small crack can lead to a permanent damage in ceramics. We also had to appreciate that for fiber reinforced matrix, it took long to break. And above all, using the research paper and also what we observed, if a fiber is really mixed well with its matrix, then the matrix is the last thing to break. after all the fibers have broken up, that's when we could see that like the brick was going to fail completely. So this we also had to actually understand the idea in mixing and malleability. And unless there was like an error in those two, it was just going to be the result. Like what I've said, that the fiber is to break first before we can talk about the destroyer of the matrix. Thank you.
Our reference list. Thank you. This was Group 6.